Hello! Today we're going to discuss about fluid mechanics. But first, let's start off by defining what fluid is. The term fluid in everyday language typically refers only to liquids, but in the realm of physics, fluid describes as any gas or liquid that conforms to shape of its container. Fluid mechanics is the study of gases and liquids at rest and in motion. This area of physics is divided into two. First is the fluid static, the study of the behavior of stationary fluids, and next is the fluid dynamics, which is the study of the behavior of moving or flowing fluids. For this video, we're going to discuss fundamental physical principles that apply to fluids. So shown here is a concept map of the main topics that we're going to discuss. We have density, which will be a significant concept for our following topics. Next, we have pressure. Under it, atmospheric pressure, gauge pressure, Pascal's pressure. And then we will talk about the Archimedes principle of buoyancy, along with the concept of flotation. Then we'll have fluid flow and continuity. And lastly, Bernoulli's equation in relation to change in speed and change in height. All of these concepts will be defined and explained for the next parts of this video, along with experiments, sample problems, and practical applications. Now, let's move on to our first topic, density.
Have you ever wondered why oil stays on top of water? Here we have two liquids of the same volume. But even when you mix oil and water together, they still separate. Oil and water don't mix because water molecules are more attracted to each other than to oil molecules. Additionally, we can see the concept of density here. The oil always floats to the top because it is less dense than water. So what exactly is density?
Density is a characteristic property of a substance. It is represented by the lowercase Greek symbol rho. It is the relationship between the mass of a substance and how much space it takes up. It is defined by the formula, density is equal to mass over volume. Meaning to say, the denser a material, the more mass it has in any given volume. In the experiment we had earlier, the oil and water actually had the exact same volume, but it turns out that the mass of water was greater than that of the oil, which explains the result on why the oil stayed on top of water. Now, to get a more feel for densities in common substances, we could start with water. Water has a density of 1,000 kilograms per cubic meter. In other words, in order to fill a cubic container measuring 1 cubic meter, it would take over 1,000 kilograms of water.
Michael is a chemist. Because of this, he tends to overthink simple things such as his coffee. He recalled placing 12.5 grams of coffee in a mug containing hot water. The mug has a height of 9 centimeters and a radius of 4 centimeters. What is the density of his coffee?
So here we can see an illustration of the problem. The mug is 9 centimeters high and it has a radius of 4 centimeters. Michael placed an amount of 12.5 grams of coffee and now he wants to know the density. Recalling the formula of density, it is mass over volume. But since we don't know the volume of the mug, we can use the formula volume is equal to pi r squared times height. So substituting the values, the radius is 4 centimeters and the height is 9 centimeters, having a total of 452.39 centimeter cube. So now that we have the volume, we can calculate for the density of the coffee. So it's 12.5 grams divided by 452.39 centimeter cube. So at the end, we get a total of 0.028 grams per centimeter cube.
This experiment shows a balloon deformed by the press of a finger and of a needle. The difference is not the amount of force that is applied, but the area over which it is applied. In the case of the needle, the force may be sufficient to pop the balloon.
Pressure is basically a measure of the amount of force applied per unit area. It is represented by this equation. Pressure is equal to force divided by area. Now the standard unit or the SI unit for pressure is newtons per meter squared. Pressure is directly proportional to the applied force and inversely proportional to the area over which it acts. Meaning to say, the greater the area the force is applied to, the less the pressure. Now this was evident in the previous experiment which we had, wherein the pen had a smaller area than the finger. Now, let's say that both the finger and the pen applied the same force onto the balloon, having a value of 2.1 newtons. And now the area of the finger was 1.0 times 10 raised to negative 4 meters squared. And as for the area of the pen, it was 2.5 times 10 raised to negative 7 meters squared. Now with these values, we can use them to calculate the pressure of both the finger and the pen. Now let's start off in calculating the pressure applied by the finger. So we just substitute the given formulas to that of the given equation. 2.1 newtons divided by 1.0 times 10 raised to negative 4 meters squared had a result of 2.1 times 10 raised to 4 newtons per meter squared. Now for the pressure applied by the pen, 2.1 newtons divided by 2.5 times 10 raised to negative 7 meters squared had a result of 8.4 times 10 raised to 6 newtons per meter squared. Now with the given values, we can conclude that the pressure exerted by the pen was greater than that of the finger. Now that's enough pressure to make it pop!
We are all used to working under pressure.
Huh?
Not that pressure,
Oh!
atmospheric pressure.
Atmospheric pressure is defined as the force per unit area exerted by the weight of air on a surface. So the weight of air is around 14.7 pounds per square inch, and atmospheric pressure is equivalent to 1.01 times 10 raised to 5 newtons per meter squared. Additionally, 1 newton per meter squared is equal to 1 Pascal. The Pascal honors the pioneering studies on fluids by the French scientist Blaise Pascal. Thus, atmospheric pressure can be defined as atmospheric pressure is equal to 1.01 times 10 raised to 5 pascals or 101 kilopascals. We can also compute for the force applied by atmospheric pressure on the palm of our hand. Now, assuming that the palm of our hand has an area of 0.008 meters squared, we can use the previously learned equation to compute for the force applied by atmospheric pressure. Now, since we know that pressure is equal to force over area, we can manipulate this equation by cross multiplication and getting force is equal to pressure times area. Now, we can simply substitute the values using atmospheric pressure and the area of your palm, and by multiplying these two values, we can get 800 newtons.
Now, let's talk about gauge pressure. Gauge pressure refers to the pressure of a system above the atmospheric pressure. It is defined by the formula gauge pressure is equal to the absolute pressure minus the atmospheric pressure.
Let's try to apply the concept of pressure on the medical field. A typical reading for blood pressure is 120/80. Do you know what these numbers mean? The value above is actually the typical systolic pressure, or the pressure when the heart contracts. It is 120 millimeters of mercury and it is about equal to 15.99 kilopascals. The value below is the typical diastolic pressure. It is the pressure when the heart relaxes after a contraction. It is 80 millimeters of mercury and it is about equal to 10.67 kilopascals. Now, when they measure blood pressure, the values given are not the absolute pressures, but are actually the gauge pressures.
So let's say that a force of 100 newtons was applied on this area, and then this area is actually 40 meters squared. Well, this area is 100 meters squared. All we have to do is to substitute the values on this formula so we can get 100 newtons divided by 14 meters squared times 100 meters squared, getting a force for F2 as 215 newtons. So what does this mean? This means that 100 newtons was applied on this area downwards, but upwards on this area, 250 newtons was exerted. Now we have here another formula for a hydraulic pump. So we can see here the distance 1 and distance 2. Distance 1 is how far the fluid is pushed down, and distance 2 is how far the fluid is pushed up. So here we have the formula to correlate these variables. So A1 times D1 is equal to A2 times D2. Now to get the value of D2, we have to manipulate the formula, and now we have D2 is equal to D1 multiplied by A1 divided by A2. So let's say that A1 is equal to 40 meters squared and A2 is equal to 100 meters squared. Now distance 1 is 20 meters, so now we have to find distance 2. So to get that, we simply have to substitute the values. So we have distance 2 is equal to 20 meters times 14 meters squared divided by 100 meters squared, getting the value of 8 meters for distance 2. This means that distance 1, at this area, the distance pushed down was 20 meters, but the distance pushed up was only 8 meters.
If something weighs more than the same volume of water does, it can basically push the water out of the way. We say it is more dense than water, and so it will sink in water. If something weighs less than the same volume of water does, it is less dense than the water, so it will float in water. The volume of water displaced by the styroball determines the buoyant force. The styroball has to weigh less than or equal to the weight of the displaced water in order for it to float.
Moving on, we have our next topic, which is all about Archimedes' principle and buoyancy. Now, before we discuss the Archimedes' principle, we shall first tackle the concept of buoyancy. We are all very much aware that some objects sink while some objects float. The reason behind as to why some objects float is because of an upward force exerted by the water. If we take a look at example number 1, we can see that a ship is floating on water. The reason why it is floating is because of an upward force exerted by the water. If we try to submerge an object into the water, we could already feel an upward force making it difficult for the object to be pushed down. Now, the upward force applied onto the object in any given volume is known as the buoyant force. It is represented by the symbol F sub P. Now we can see that buoyant force is applied here in illustration number 2, or in example number 2. If we try to submerge a basketball underwater, you would feel that there is an upward force exerted by the water, which is the buoyant force, making the basketball more difficult to be pushed down. Buoyant force is basically defined by the formula: buoyant force is equal to the density of the fluid times the volume of the object times the acceleration due to gravity, and the SI, or the standard unit for buoyant force, is Newton. Now, Archimedes' principle is also known as the law of buoyancy. The principle states that the buoyant force applied to an object is equal to the weight of the fluid that the object displaces. Displacement in this context refers to when an object moves a fluid, it can occupy the volume that the fluid originally occupied.
Have you ever noticed that if you place your finger partially on the opening of a faucet, the speed seems to increase? Now we're going to talk more about this situation regarding our topic, fluid flow and continuity. Here we can see a diagram of a pipe with different diameters. Now this is cross-sectional area 1, which is the circular part, the bigger circular part, and cross-sectional area 2, which is the smaller circular part. Now, water is actually moving through these pipes with velocity 1 at this area and velocity 2 at this area. Now let's go to the volume of water passing through each areas. For area 1, the volume of water is equal to area 1 times velocity 1 times the time given. Now let's take note that capital V represents volume and small letter v represents velocity. For the volume at this area 2, we have volume 2 is equal to area 2 times velocity 2 times the given time. In our previous lessons, we can recall that mass is actually equal to density times volume, but we can actually substitute the value of volume using these formulas. So now we can get mass 1 is equal to density times area 1 times velocity 1 times the time given. And in turn, mass 2 is equal to density times area 2 times velocity 2 times the time given. Now, the formula for continuity actually states that when a fluid is in motion, it stays in motion in such a way that the mass is conserved. So that means that regardless of the different diameters of area 1 and area 2, the mass is still the same. So that means that mass 1 is still equal to mass 2. So we can actually equate these two formulas as equivalent to each other. So now we can say that density times area 1 times velocity 1 times the time given is equal to density times area 2 times velocity 2 times the time given. So now we are left with our equation for continuity. So that's basically density times area 1 times velocity 1 is equal to density times area 2 times velocity 2. Now you're probably wondering why we haven't cancelled out density like with what we did with time. Well, this is because some fluids are compressible, specifically gas, meaning that the density for area 1 might be different for the density for area 2. So, there's actually a different case for incompressible fluids, specifically liquids. Since liquids are practically incompressible, this basically means that their density stays the same all throughout. So we can cancel density and be left with the formula A1 times velocity 1 is equal to area 2 times velocity 2. But this only applies for liquids.
Bernoulli's principle tells us that air that is moving at high speed has lower pressure than still air. This experiment shows that the air moves around the ball to create a pocket around the ball of low pressure air. When the ball moves to the side of the pocket, it will be pushed back in, and the upward force from the airstream keeps the ball aloft.
So here we have the formula for Bernoulli's equation. The left side of the formula represents point 1 and the right side of the formula represents point 2. So here we have several terms. So this term and this term represents the pressure energy for both sides and has the variable pressure. This term and this term represents kinetic energy for each side and is equal to 1/2 times density times velocity squared. Now this term and this term represents the potential energy and is equal to density times acceleration due to gravity times the height.
Let's look at the application of Bernoulli, which is in the field of cardiology. We'll start with a schematic of the right side of the heart with our right atrium and right ventricle separated by the tricuspid valve. Now in most people, even in completely healthy people, there's some amount of blood, typically very small, that travels backwards through their tricuspid valve, moving from the right ventricle to the right atrium during systole. Normally during systole, blood travels from the right ventricle into the pulmonary artery onto the lungs, and we like to think that there's nothing going backwards, but a tiny amount does, even in normal people. This is called tricuspid regurgitation, and measuring the velocity of this regurgitant jet provides important insights into the human dynamics with the help of Bernoulli. To measure the velocity, we put an ultrasound probe against the skin of a patient's chest wall and it fires sound waves into the body. Each time the sound wave encounters a different structure, some fraction of that wave gets reflected back. If the reflected wave has a different frequency than the wave released by the probe, it means that something is either moving away or towards the probe. This is an example of the Doppler effect, which will not be our focus here. But the important point is that velocity can be measured accurately. But what do we do with it? That's right now Bernoulli with a point in the center of the right ventricle, or RV, as point 1, and a point just adjacent to the valve within the right atrium, or RA, as point 2. First, the difference in the vertical height between these two chambers relative to the other pressures involved is trivial, so the ρ-gy terms can be ignored. Let's rearrange terms. Since points are adjacent to the tricuspid valve and the point RV is some distance away from the valve, then the velocity RA is much greater than the velocity RV, even more so when these velocities are squared. So the term 1/2 density VRV squared can be ignored to achieve an approximation. This then leaves pressure RV minus pressure RA is approximately equal to 1/2 density times VRA squared. At this point, let's use a number of relationships that we know first. Pressure is a measure in pascals, which is newtons per meter squared. Density is in kilograms per cubic meter, and velocity is in meters per second. 1 millimeter of mercury is equal to 133.3 pascals, and the density of blood is normally about 1060 kilograms per meters cubed. So if we incorporate this information, we find that pressure RV in millimeters of mercury minus pressure RA in millimeters of mercury approximately equals this times VRA in meters per second squared, which becomes the pressure gradient across the tricuspid valve during systole in millimeters of mercury is approximately equal to 4 times the velocity of the tricuspid triggered jet squared. This extremely parsed down version of Bernoulli is sometimes referred to as the simplified Bernoulli equation. So why is it so special? If you remember, you know that we can use the concept of hydrostatic pressure to estimate a person's central venous pressure from the height of jugular venous distension. If you remember, you know that we can use the concept of hydrostatic pressure to estimate a person's central venous pressure from the height of jugular venous distension, and central venous pressure is equal to the right atrial pressure. So adding the central venous pressure to lateral tricuspid valve, pressure gradients give us an estimate of right ventricular systolic pressure, which in the absence of pulmonic valve disease is equal to the pulmonary artery systolic pressure. In other words, combining hydrostatics and Bernoulli allows us to non-invasively estimate the blood pressures within a patient's pulmonary artery, which gives us insight into a hugely diverse collection of cardiac and pulmonary diseases.
Before we officially end our lesson about fluid mechanics, here are some few points you have to remember. Thank you for watching.